So it's a pleasure to introduce our last speaker for this afternoon session, Georgios Pappas from Michigan State University. He's made many fundamental contributions over his career to the study of the arithmetic and geometry of Shimura varieties, and today he'll speak on arithmetic models of Shimura varieties.
Thank you very much, Andre, for the introduction. It's a great honor to be speaking here. I hope my effort is up to the task. So I will talk to you about recent work on arithmetic models of Shimura varieties, and I will start with the most classical example, that of modular curves. So we usually, as usual, we start with a complex upper half plane on which have the action of SL2R by fractional linear transformations. Let's pick a prime number and consider one of the standard congruence subgroups given by matrix and SL2Z, which have C entry divisible by P. This acts on the complex upper half plane, and we consider a modular curve given as the quotient. Now, it's a classical fact that this parameterizes isomorphous classes of elliptic curve isogenies of degree P, where the elliptic curves are over complex numbers. But we are interested in some kind of an integral structure on that curve. And the first known kind of integral structure is given by the modular polynomial. So this says that the curve has a planar model over the integers given by the vanishing of the modular polynomial. Now, unfortunately, the modular polynomial is very difficult to calculate, compute, or do anything with, really. The only kind of maybe useful thing for us is the following congruence, that if you take it mod P, is congruent to this very simple polynomial. And this actually is a result that it's in the flavor of what's coming up later. This can also be interpreted as the Eichler-Shimura congruence on the modular curve. Now, the more modern point of view leads to the following theorem that starts with Shimura, Egusa. Maybe this form is in a letter of Deling, and it's spelled out in the paper of Deling and Rappaport. It says, let's take the prime to be bigger than 5 or equal to 5. Then there's a model over Z, and now model I mean in the scheme theoretic sense, such that if I take the reduction on another prime, different than P, then I'm looking at a smooth curve over a finite field, and if I take the reduction modulo of that prime P, I have a singular curve that has two smooth irreducible components that intersect transversely like this. And in fact, you can say the following, which is again a prototype of the results that would follow, that this curve is locally isomorphic in the étale topology to these very simple intersecting lines. Okay, the proof, well, it's going to be a very quick sketch. The idea is I can define the moduli scheme of elliptic isogenies of degree P over Z, and then by studying the deformation theory of these isogenies, I can determine the local structure at P or at L. Okay, so now I'm moving on to the main topic, which is that of Shimura varieties, and here I will use Deling's very elegant but also difficult to understand formalism. So we look at pairs of the reductive, connected reductive group over Q, and conjugacy class of the homomorphism of algebraic groups over R from this restriction of scalars that's usually called the Deling torus, that satisfies certain conditions that I'd rather not describe right now. I'm just going to say that the conditions imply that X is a disjoint union of symmetric Hermitian domains, and therefore there's a complex structure there, and the real points act transitively by holomorphic automorphisms. And so let's fix now a Shimura datum, which is that pair. And we also choose a compact open subgroup of the finite adelic points of the group G, which we'll call the level subgroup. Now maybe this F should be down there, I mean finite adels. And now here's the definition of Shimura variety as a double coset, where we take the product X cross this cosets of the adelic points modulo K, and then I act on the left by the rational points of the group, where the action is diagonal there. on X and on the Z of AF by the embedding of Q into the Adels. Okay, so. All right, so some basic properties of the Shimura variety construction given in that form. So if I have a smaller subgroup, then there's a map like that. Then also what you can easily see by using some approximation theorem is that this is really a finite disjoint union of quotients of symmetric Hermitian domain by congruence arithmetic groups. So this is the most common way to understand maybe those spaces, but the formalism of Deligne has many advantages that I'd like to use in our presentations here. So, okay, what is harder is to show that this is actually a union of complex algebraic varieties. This was proven in the 60s by Bailey-Borel, and we've seen this in Peter's talk too. And so let's continue with the pair, because now I want to describe the main theorem of the theory of Shimura varieties over number fields, I guess. So I take the complex points of the linked torus, and so I get this homomorphism like that. And so I set mu to be what's given there, and so I get an algebraic co-character of that type. It goes from C star to the complex points. And this is actually minuscule. This is implied by the axioms that I omitted mentioning in the definition of Shimura variety, but what this means is that mu pairs with every root of the group to give you 0, 1, or -1. Somehow mu is rather small in some sense. Okay. So here's the important definition. The reflex field is the field of definition of the conjugacy class of that co-character mu, and it is a number field. And so we keep this, remembering this field. And associated to this data, I also have the homogeneous space of parabolic subgroups of G of type nu, which is a smooth projective variety, again defined over E, and the corresponding complex variety is the compact dual of the symmetric Hermitian domain X. And so here's the main theorem of maybe the beginning of the theory of Shimura varieties, or due to many people over the years, started from the 60s and finishing in the 80s by Milne and Borovoy. The Shimura variety has a canonical model as an algebraic variety defined over that number field. And now maybe it's appropriate here to discuss the various types of Shimura varieties or data, and this will play a role in the talk. We have PL, Hodge, abelian, and finally general Shimura varieties. And so Shimura varieties of PL type are really moduli space of abelian varieties with polarization endomorphs and level structures. And these are the most common examples fit in this category. So modular curves, Ziegel modular varieties, Shimura varieties for some unitary groups, etc. The most useful ones, maybe. Shimura varieties or Hodge type are more general. They're moduli space of abelian varieties, but now you ask to have distinguished Hodge cycles and, of course, level structures. And I will say something abelian type later. And, of course, general is just general. Okay, so now let's discuss the main topic of this talk, which is the arithmetic models. So our goal is to describe good models of the varieties, but now over the integers. We have them over number field. I want them over the integers. And we'll work prime to prime. So we fix some notations here. I pick a prime that's sitting over my fixed prime P. I take the completion of the reflex field, the integers of the completion. I pick a uniformizer, denote the residue field. And also I pick a level subgroup that has those properties. So this is just for simplicity. I ask that the prime P part of a level subgroup is sufficiently small, so what I say is exactly correct, or more or less. Okay, so we want models, and I will denote the models, I hope it's visible, by this calligraphic S. So SH is the Shimura variety, calligraphic S is the model. I want the models over a completion of the field, so these are schemes that have this property. I want them to be compatible for varying the level subgroup K. And usually we'll fix later the level subgroup at P, and we just vary the prime to P level, Kp. But let me say what the wish list of what I want from these models. I want a good description of their points on their special fibers over the algebraic closure of a finite field. I want a description of the local structure, like how singular they are and how to tell the singularities. And finally, some sort of characterization among all the possible models that you could have, because you could have many, say, by blowing up things in the special fiber. Okay, so why do we want and how do we want to organize these answers? A motivating application is to Langlands' program, relating automorphic representation and Galois representations, and very often this is expressed by, or like the first step to express this is to try to calculate the zeta functions of the Shimura varieties. And this is done by a standard method in which you need to know the points, to count the points over finite fields, maybe look at the contribution of singularities, combine Lefset's fixed point formula with the Arthur trace formula, and get somewhere this way. It's pretty complicated. But somehow the motivation for what kind of description we want is we want a description that could be useful in applying that method, more or less. I mean, this is not, of course, the only application of these models, and I'm listing some other applications here. There are applications to the p-adic theory of automorphic forms, like previous talks we've seen by Piloni. And also proving formula, I'll just say a Gross-Zagier type for special values of derivatives, or in general looking at all this Kudla program of intersections of special divisors or special cycles. Okay, so the first kind of structure or attempt to find some structure in this theory of reduction was this conjecture that is a vague conjecture, like a first vague conjecture of Langlands, and then was formulated more carefully in the paper of Langlands and Rappaport, that starts as follows. Now let's suppose that the group extends to a reductive group over ZP, and I pick the level subgroup at P to be the ZP points, and now the conjecture is that there is a smooth model, actually, in that case. So there is good reduction in that case, and in fact, you can pick the smooth model to be canonical. I'll say something about this later. And then one asks for a description of a set of points with the Heike and the Galois action, which is pretty complicated, but I can just like show you the structure of the formula that Langlands and Rappaport conjectures. It should be written as a disjoint union over this classes phi. So phi runs over isomorphs classes of what I call G pseudo-motifs. Now you can think of them as isogeny classes of abelian varieties. And then there is some quotient there by an algebraic group over Q, which is the automorphism of the fixed motif in the class that you're picking there. And then I'm giving you some kind of vague description of what these sets that appear in the formula are. So when I state it like that, it's not a precise statement. It just gives you an idea. It's not a precise statement because I'm not telling you exactly what are these isomorphisms there and how they are given by the theory. Okay. So, oh, I forgot. The W is the ring of Witt vectors. Now, I'm not going to emphasize this part of the theory, so it's not so important to discuss this. I just need to give you a feeling of what you expect. There is some structure, there's some description where it's motivic and group theoretic. Okay, so the one important result in the last 10 years is this theorem of Kissing that basically says that this conjecture is true when P is odd that G of X is of abelian type. Now notice there is an asterisk in true, and this is an explanation. So Kissing first modified the original conjecture of Langlands-Rappaport, and then doesn't exactly prove it on the nose. It proves a statement that resembles what I wrote before, but without specifying the isomorphisms very well. What he proves is good enough for applying to the Langlands-Kottwitz method to get a zeta function anyway, if you want. There's a lot more work, but it's good enough. So here's some more explanations. So we say it's abelian type, when roughly speaking is isogenous to Shimura datum of Hodge type, and that's all I'm going to say. And this is the case for most G where the Lie algebra is classical. So this takes care of all the cases we need somehow. And then the precise notion of canonical is due to Milne. Langlands had a very vague kind of idea of what this would be, I think. And then, so Milne characterizes the models by a Néron type property that makes them unique. And here's some more information for Siegel model varieties. We have follows by work on Mumford. And then it's important to mention earlier work on B. This is the description of the points by Zink, Riemann, Kottwitz especially for PL Shimura varieties, and also on the existence of models by Vascu. So this is the situation where we expect good reduction. And now I will kind of continue with the following questions. What if the group does not extend to a reductive group? So this is going to be the case for a finite set of primes at which the group is ramified. Of course, the previous theorem takes care of the infinite set of primes, but there's still these nasty primes you still have to worry about. And what about other subgroups, KP, not just like the points of the extension of the group, but kind of deeper level subgroups? Okay, so now most of the rest of the talk will be about a class of subgroups for which there's a good answer to this construction of models. This is the class of parachoric subgroups that's provided by Bruchate's theory. So here's the first important fact, that the group always extends to a parachoric group scheme. So there's always something like that. It maybe does not extend to a reductive, but it does extend to this. This extension depends on a choice of a point in the building, and I'm not going to say much about that. I'm just going to say that the group acts on the building, and so the group scheme that I'm extending my reductive group to is constructed as a smooth connect affine group scheme over ZP, which has the following properties: extends G, and the ZP valued points is the connected stabilizer subgroup of X in ZQP. So as I said, the group acts on the building, a part of the group fixes X, and basically up to connected component, whatever that means, this is what GX of the ZP is. So I'm kind of being a little bit, I'm cheating a little bit here for people that know this, but it's an easier way to understand what's going on by a small cheat, so, okay. And so the definition is a subgroup is parachoric if it's equal to one of these guys. Okay, and so here's some examples. When we have classical groups, I'm looking at connected stabilizer of chains of lattices. And so, for example, for GL2QP, you have two types of parachoric subgroups, either maximal, in which you stabilize a ZP lattice in QP square, or an Ivachori where it's the intersection of the stabilizer of two adjacent lattices. And so the expectation now, going back to Shimura varieties, is then if you pick such a subgroup, then we should have natural good models where the étale local structure explicitly depends on that pair, or oops, here it is. So I'll use this notation, mu v, to be the conjugacy class over the completion of the reflex field given by mu. Mu was a conjugacy class over E, and now I'm just looking at the completion of that. Okay, so this is the vague expectation. Now I will make this more precise. So here's a local, what I can call a local model conjecture due to Rappaport modified by me at some various stages. So we fix a Shimura datum in parachoric subgroup. So we first kind of conjecture the existence of a flat projective scheme over the integers. This is the so-called local model that has a left z action with the following properties. The generic fiber should be the variety of parabolics, which was the compact dual of the symmetric domain, at least over that completion. And this doesn't work? Oh, okay. So the special fiber is reduced. And then there's a description of the set of points of a special fiber as the union of orbits in what is essentially a affine flag variety, which are bounded by this conjugacy class. So what you take from this, if this looks too complicated, you're looking at a very specific integral model of a projective variety of parabolics, which is a simple thing. This projective variety of parabolics is usually like something like a Grassmannian or of some type. Okay, and part two that relates to Shimura varieties, that should exist what I call a relatively proper system of models of the Shimura variety. So I say system because now I'm allowed to vary k. I fix the level subgroup at P and I vary the prime to P level subgroup that has the following property. For each closed point on the Shimura variety, there is some closed point on the local model with matching at all local neighborhoods, which means the singularities are the same. And I explain a relatively proper system. This kind of attempts to formulate a Néron type criteria, but it's kind of weaker, that the limit satisfies the evaluation criteria of properness for DVRs of mixed characteristic. So now this is sort of telling you that you're not allowed to throw away parts of a special fiber you don't like. So you have to have something that's really all of it is there. So there's a more precise but important variant of two, that there should be a system like that, together with a diagram of this type, where the map, at this point, to use the laser, this map is smooth and equivariant, and this map is a torsor for a smooth quotient of a group scheme. And moreover, if you look at the generic fibers, this diagram should be the principal bundle, automorphic bundle over the Shimura variety, which has a canonical construction coming out of the, say, of the Borel embedding of the Hermitian domain in its compact dual. Okay, so you can easily see that what I call 2+, which is this local diagram, local model diagram property implies 2, because both of the two maps, pi and q, are smooth. And so if you have smooth maps like that, the singularities of the left and the right match. And actually 2+ manages to give you integral structure on spaces of automorphic forms by taking various representations of the covering group in the torsor. The same way as you get this from the principal automorphic bundle. Okay, so here's the results about this conjecture. So first is theorem joined with Xi and Zhu. So we assume G splits over tamely ramified extension. Then there is a local model with these properties that I listed before, A, B, and C. And now I should mention here when, this is a very technical point, but when P divides the order of fundamental group of a derived group, we need to adjust the definition it was given in that paper, and this was done in my joint work with Xuhuahe and Rappaport very recently. And now here's an idea of the proof. So I will assume that derived group is simply connected for simplicity. And so the first thing we do is we extend the parahoric group scheme to an affine smooth group scheme over a two-dimensional base. So it was over ZP. We extend over ZP bracket U, this affine line over ZP, using Bruch-Hatitz's theory. Now the extension is in this sense, that if I restrict on U equals P, I get back the original group. So I don't restrict on U equals 0 in my setup, I restrict to U equals P. And the tameness assumption is quite important for this construction. Okay, the second step is we look at the Bayesian-Drinfeld affine Grassmannian over this affine line. And now this is maybe, for a number theory section, this is like a tough sell, but this is, explain this. So this parameterizes isomorphous classes of triples where you have a torsor over Y, a point of Y, and a section of the torsor, so a trivialization of the complement of that point. So I'm kind of being a little vague here. I'm not writing this like exactly the functor represented, just giving you the idea. Okay, so you can now easily see that the homogeneous space of parabolics embeds into the fiber of the Bayesian-Drinfeld Grassmannian over the completion of the reflex field by this base change. And the definition is that the local model is the reduced Zariski closure of that embedding. So this is a very cryptic kind of definition. It uses the Bayesian-Drinfeld Grassmannian, which is an infinite dimensional object, to construct this thing that's actually relatively simple. Should be a simple variety. It's, after all, an integral form of the homogeneous space. But it actually, with this definition, you can manage to prove all these properties. So, for example, property A follows easily, because I said generic fiber, I take the closure, so there's the generic fiber. But actually, the other properties are quite hard. And this depends on, so the way that this was proven is as follows. So you have to check that two Hilbert polynomials are the same. These Hilbert polynomials are obtained by certain ample line bundles on this Bayesian-Drinfeld Grassmannian. And this equality is what is called, was called the Coherence Conjecture, myself and Rappaport. And you can prove this in the equal characteristic case. You just kind of do a shift in the equal characteristic case. And this was proven by Zhu using methods from the theory of geometric Langlands correspondence. So it's a complicated and difficult proof that involves a lot of ingredients. Okay, so here's some remarks. First of all, there is this restriction of the group being tamely ramified. Now, Brandon Levin has an extension of the construction to most wildly ramified groups. Let me explain what I mean by most. So he can allow to take restriction of scalars from a wild ramified extension of something that's tame. And when you do this, you pretty much cover all the wild cases except for small primes. 2 and 3 actually are the only cases that are missing. On the other hand, this is like an ad hoc construction. It's not very satisfactory, and I have to say this problem is not very well understood yet, how exactly to give this construction, I think. And there is some progress in that. So Peter Solze gives a characterization of the local models, which is something that's missing from my discussion so far. So he says that local models are the only flat projective G-scheme that satisfy properties A and B. So here, correct generic fiber, reduced special fiber, and an extra property that uses more technology, though it's expressed in terms of the diamonds, and the diamonds, associated diamonds, should be embedding in a diamond Bayesian-Drinfeld affine Grassmannian in a way that resembles the embedding in the definition. So this does not define those models. It just proves that they are unique if you can compare them and you can check that this definition is satisfied. And this extra property And therefore, a unique characterization of the local models were recently proven in many cases by he, myself, Rappaport, and independently by Lorenko. Okay. So I guess that's it. So the second theorem that kind of connects now all this to Shimura varieties. Up to now, this theorem was nothing about Shimura varieties. Is the following. So again, we assume G of X is of abelian type. G splits over tamely ramified extension, P is odd, and then the local model conjecture is true, provided we pick the local models that were given by the previous theorem. So this local model conjecture, I remind you, had this other part that relates to the Shimura variety. So it says that there's a model of a Shimura variety that has the same local structure as the local model. Okay, remarks. So this is the local model conjecture with property 2 in the theorem, but in fact there's the more precise conjecture with the local diagram property 2, what I call 2 plus, that was this diagram, also holds, but the situation is not so happy with this. We need some additional technical assumptions that look like difficult to completely remove. So at this point. And now there is a history in this. So in the case with Shimura varieties of PL type, then integral models, local models, and the diagram as in 2 plus were given by Rappaport-Zink, and this just directly uses a modular interpretation. And in this case, they give local models explicitly by linked Grassmannians for lattice chain. But so these are given kind of ad hoc, and you don't know things like the special fiber is reduced or how to parameterize the points of the special fiber. So you don't know properties B and C for those models or the flat closures. So on the other hand, when G is tamely ramified, the flat closures of the Rappaport-Zink local models agree with the ones we gave, and so you get extensions of all these results. Now I'm going to say something about the proof of this second theorem. Now this is quite complicated. I'm just going to give like a sketch, some vague idea of some ingredients that go into this. So the first kind of ingredient is to reduce to the case where you have Hodge type Shimura variety. So remember, the theorem talks about abelian type, and abelian type are isogenous to Hodge type, so we need to go from abelian type to Hodge type. And this uses some integral version of the link sphere of the connected component of Shimura varieties. Because of this isogeny property, the connected component, meaning like a connected component of Shimura variety for Hodge type, relates to easily, or more or less easily, to the connect component of the Shimura variety for the abelian type. And then after that, you do some kind of induction to generate the whole Shimura variety. So anyway, this is technically complicated, but in some sense, like, can be called maybe a routine. I'm not sure. But now let's continue with the Hodge type, where all the difficult things come in. And so for simplicity, I assume the reflex field is Q. And so now I'm at Hodge type. And so there's an embedding, by definition, in the Ziegel-Shimura variety. This is given by picking a symplectic representation of the group. Remember, the Shimura variety of Hodge type is a moduli space of abelian varieties with Hodge cycles, and this interpretation is what gives you the embedding. Okay, of course, now the Ziegel-Shimura variety is the moduli space of principally polarized abelian varieties of that dimension. And this modular interpretation makes sense over the integers, and so we get a good model that was mentioned before in the talk is the canonical, maybe smooth model of the Ziegel-Shimura variety. And so we have a good model for that, and somehow I want to use this good model to get a good model for my Shimura variety that embeds into it. That's the idea. Now, like, of course, there are many embeddings. And now we have to be really careful and choose a good embedding, meaning I want to choose the simplectic representation that gives the embedding carefully. And the two main things that I want are the following. First, I want the group scheme that gives the level at P to embed, I'm just going to say nicely, in a reductive group that extends the symplectic group of GSP2G, I guess, where G is the genus that we're talking about here. And also I want to make sure at the same time that the local model embeds in the corresponding local model for a symplectic group, which is a Lagrangian Grassmannian. So this is a difficult thing to arrange, but it's possible. And now what you do is, after you make sure that the embedding satisfies those, then here's the definition. The model is the normalization of a Shimura variety in the integral model of a Ziegel-Shimura variety. And now, of course, what remains to show is, and I emphasize after making this so good embedding, A and B, that these have the same local structure. Now, that could be nonsense if you didn't know that M-log, the local model, is normal to begin with, because, right? But it is normal because it has special reduced fiber. So this is a check that we're not being crazy here. Okay, and so now this uses a lot of like deformation theory, and the problem is, the main problem is we don't really have a very good modular interpretation, because the notion of the Hodge cycle does not extend well in the mixed characteristic case. So it's difficult to handle. You have to go around about ways. So we have to use what I call here crystalline avatars of the Hodge cycles. And so we'll determine how this control the tau local structure by deformation theory. So I'm just going to mention various ingredients we use. So first is integral p-adic Hodge theory. This fabulous Broyle-Kissing models. And then a purity result. That's kind of an interesting thing. But if you have a parachoric torsor over I take the completion here, not a ZP completed power series at U, and I take away the closed point. This extends to the whole thing, and they are actually then trivial. So with those two ingredients, we deduce something that I only describe roughly, but the crystalline realizations of the Hodge cycles can be put in standard position. I don't think I have time to explain what this means in detail. And after you do this, then you can use the Hodge filtration of the abelian scheme that given by your point to get a corresponding point in the local model. So you kind of made a start, you match the point to another point. Now you need to match the tau local structure, so you need to match the completion at one point to the completion of the other point. And so studying completions is done by deformation theory. And so it's enough to show how we can construct deformations of the point in the integral model from the point in the local model. And here's a vague idea. So there is this Grothendieck meshing theory. It tells you that if you look at the de Rham cohomology of abelian scheme, this is a crystal, and the deformations are given by deformations of the Hodge filtration. So if I deform the Hodge filtration, I get a deformation of the abelian scheme. Now, here we need to be careful, and the idea now is that we need to show that if the Hodge filtration stays in the local model, remember the local model embeds in the Lagrangian Grassmannians, so it parameterizes filtrations again, or like subspaces rather, and then the corresponding abelian scheme stays in the integral model. This is the hard part. And Okay, so there we switch to a p-divisible group and use a Zink's theory of displays for p-divisible groups. It's pretty complicated, but I'm just going to say the following. One of the essential ingredients is the points of a local model give values of a functor that looks like a Witt vector affine Grassmannian for Z. So this relates to this interpretation of a local model by Solz's property, somehow, implicitly at least. And so we get Zink displays with this structure, and then you can show that you get p-divisible groups that actually stay in my integral model. Now, the difficulty, I'm just going to say one more thing about why this is difficult. The problem is the integral model was defined by this operation taking closer normalization. So it's kind of hard to know when a point stays in the normalization of something that's coming from the fiber. This is why you have to do a lot of tricks here. Anyway, so okay, and this is the completion of the proof. Let's do some examples in the time we have, really quickly. First, I take ZL2. Here's my X. The compact dual is just P1. I take the Ivachori subgroup, which is the stabilizer of this lattice chain. Then I have just the modular curve that I started with. Now, the local model is the blow-up of P1 at the close point of the fiber. And if you look there, you'll see that you can calculate this easily and find an open subscheme that contains the unique singular point that's given by this. The singularity x times y equals to p, and so we recover the picture of the theorem. So here's another example. I take a real quadratic field. I take a ramified place. The group is a restriction of scalars from this. I take again Ivachori type. This is a Hilbert modular surface with p-level structure where p is ramified. I'm just going to give you some examples. So the local model is now a model of this surface given by a restriction of scalars of p1. And in this case, you get this weird singularity. Now notice that this has two components that intersect. Like if you set both x and x plus y is equal to 0, I'm talking about the special fiber. So you intersect on y times z equals 0. So you have two things that intersect on two other intersecting things. So it's kind of cool shape. And this is a nice example of something that's not of PL type. I take the Z-spin group, dimension 2n. I forget, I should say the signature is 2n minus 2, 2, and then the domain is of type 4, and so the compact dual is a quadric. Let's assume the split over QP, and then there's lattices that have these properties. So both, there's a lattice lambda 0 that's self-dual, and a lattice lambda 1 that's self-dual up to pi, that's called like pi modular. And I take the paraphoric subgroup to be the intersection of stabilizers. And then the local model is a model of the quadric. And in this case, we find semi-stable reduction, which is kind of a strange thing that we didn't expect. So you have two smoothly reducible components intersecting transversally. And so therefore, it's true for a Shimura variety. And this was observed and shown by Faltings relatively recently by a different method. Okay, so these are my examples, and I only have time for some comments. So the first comment is that now you can make a little bit of headway towards calculating the local factors of the zeta function, a place of paraphoric Batt reduction. This is a very complicated project, and maybe it's not entirely the way to go every time, but still. So the description of the singularities gives you a way to calculate a semi-simple trace of Frobenius on the nearby cycles and verify conjectures Kottwitz and Kottwitz-Haynes. And these conjectures predict, I'm just reading at this point, the test functions that should be inserted in the comparison with the Arford trace formula. And the most recent result is due to Haynes and Richards recently that do this. Now, this is just one small ingredient. You don't have to go this way. There's also the method of Solze that is maybe different, but some aspects of this theory are useful in that method anyway. So a second remark is some of these constructions also are similar and give you results for local Shimura varieties, so Rappaport-Zink spaces and other related spaces. In fact, there are many, many spaces that have the same type of structure. And in fact, even in spaces, deformations of Galois representations, you see local models playing a role. This appeared in work of Kissing and also Karayani, Levin, and more recently of Lele, Hank, Levin, and Mora, and others. And I'll finish, I have like a couple of seconds, with some problems or questions. First is to obtain the conjecture Langlands-Rappaport in this case. This is not done. The statement goes through without problem. There is some progress by Stuart, Marx, Kissing, Rongzhu. And then give actually characterization of the model and show that they are canonical. And I think that should work if you insist that the local model diagram is exactly as it is. Extend to the wildly ramified case. Get results for deeper level subgroups. This is probably too hard and maybe not so useful, but I thought I put it on because it's interesting. And this is very interesting, but maybe nobody has an idea to handle not a billion Shimura data. And finally, this is like a Hail Mary type of question. Are there spaces that play the role of Shimura varieties or the integral models where mu is not minuscule? You always being handicapped for Shimura varieties to insist that mu is small, and in other situations, like in Peter Solz's construction, you don't have this restriction. One might wonder if this is possible to do in this Shimura variety setup. And thank you very much. That's a talk. Thanks.
Are there any questions for the speaker? So if there are no questions or comments, I'd like to thank George for his lecture.